Hey math people, L'Hopital time. If you're looking for a limit and you have a ratio of two functions of the thing you want to find the limit of, and you get one of the bad guys. So the bad guys are indeterminates. That's the official word for them. If you get 0 over 0, infinity over infinity, or negative infinity over infinity, these guys are bad. You can't do math with them. They're not real numbers. They're indeterminates because the idea behind them is that two ideas are conflicting. If you take 0 over 0, you look at the numerator, it's tempting to say that this thing is 0. Well, if you look at the denominator, it's tempting to say this thing's also infinity, because if you divide by 0, 1 over infinity, it's like infinity. So since you have two different ideas kind of tackling it at the same time, you really can't determine what it is, so hence indeterminate. Anyways, if this does happen when you're dealing with a limit, fret not, you can do an easy thing. If you just take, these are primes, if you just take the derivative of the top and the derivative of the bottom, that is fine. That'll be your answer. You should look up the proof if you're curious as to why this is the case. It's kind of cool, a little abstract. Not the point of this video. Just want to show you four quick ones. Just a little bit of practice as we gear up for AP season or testing season. I don't know. This is applicable for both, university level, right, and high school level with AP. So I'll show you what AP needs. AP is a little picky, or College Board is a little picky with how you apply L'Hopitals. You need to make a statement. If you don't make a statement that you're applying L'Hopital, then they could technically take off points. So I should attach 4 problems. Look at the description for that. First one, limit. So we'll call this number 1, I guess. Limit as x approaches 0 of e to the x minus 1 all over sine x. All right, so we have a ratio. We have two functions. We have f of x, which is e to the x minus 1, and g of x, which is sine x. If I were to attempt direct substitution, I plug in 0 here. E to the 0 is 1. 1 minus 1 is 0. And likewise, sine of 0 is just 0. So 0 over 0 is the case that we're running into. We need to apply L'Hopital. This is how you should clarify to the reader that you're going to apply L'Hopital. This is how I do it. There's different styles for it. This is just trying to make College Board AP happy in terms of their requirement for it. You should make independent statements. So maybe in blue I'll do that. So you should say, since the limit as x approaches 0 of e to the x minus 1 is equal to 0, and we'll write and, the limit as x approaches 0 of sine x is equal to 0. What does this imply? This implies that we can apply L'Hopitals. A little annoying, right? A lot of writing just to say, hey, let's do L'Hopital. Just to make the reader happy. This is like a case-by-case thing. Maybe your professor does not care at all about this if you're in a university. So some people do, is all I'm saying. So sometimes I see people do this up top on the equal sign. They just put a little L hop just to say, hey, I'm doing L'Hopital. That's cool with me, but like I said, it's case by case. So here we're going to say, all right, well, this is the same thing as a limit as x approaches 0 of, what's the derivative of e to the x minus 1? We know that the derivative of e to the x is e to the x, and we know the derivative of a constant goes away. So numerator is just e to the x. Down in the denominator, derivative of sine is cosine. So finishing up this problem, plug it in 0 here. E to the 0 is just 1. Cosine of 0 is just 1. And hey, my answer is just the number 1. All right, so looking at the next one, we are approaching 1. Up top you have x minus 1. You can already tell it's going to be a 0. And down below we have the square root of x plus 3. And then subtracting off 2. And I believe this one can be solved using a conjugate approach, but let's pretend I asked you specifically to do L'Hopital here. In which case, let's write a statement. since the limit as x approaches 1 of x minus 1, this is 0 for sure, and the limit as x approaches 1, actually I didn't check to see if this is 0, I just assumed it was. If you plug in 1 here, 3 plus 1 is 4, square root of 4 is 2, 2 minus 2 is 0. This implies that we can apply L'Hopital's. Alright, so limit as x approaches 1 does not change. Looking at the numerator, that's an easy derivative. Derivative of x is just 1, and derivative of the constant nulls out, it's 0, goes away. Down below, we have to do a little bit of thinking. So what we should do is, maybe in different color here, do it in purple. I'll try to show you a way that I would find this derivative. I would say it's better to observe this as x plus 3 all to the 1/2 power. It's going to help you find the derivative a little bit easier because we can just sneak this up front. We get 1/2 x plus 3 all to the -1/2 power. And this is a constant. So just to clarify here, I'm taking the derivative of this expression, sneaking in a ddx. This is equal to half times this expression. Now I'm using power rule, subtracting 1 from the power, and sure enough, the derivative of a constant is 0. Lastly, I should apply chain rule. However, the inner expression, the derivative of x is just 1. So if I did apply chain rule, it's like a times 1 off to the side. But obviously, if you multiply by 1, it's not going to change your expression. So with that said, this is just kind of negligible in that sense. All right, so now what? Let's put this up here. So we have 1/2. And then down in the denominator for this, we have the x plus 3 all to the 1/2 power. So I brought it down to the denominator. I guess I can show that right here. So since it's a negative exponent, I can bring it to the denominator of this fraction expression. And here I have the x plus 3. It is now a positive. So negative up top, positive down below. All right, this is just the reciprocal. When you have 1 over a thing, it's just saying, hey, take the reciprocal of that thing. So the limit as x approaches 1, take the reciprocal of this expression right here. So the reciprocal of this expression, it's just flipping it on itself. It's actually like the double reciprocal, which is your back to itself. This is the expression, 2. And if you don't mind, I prefer the square root now that we're done with the math. Instead of 1/2 power, I'm going to do the square root of x plus 3. And now a direct substitution should work. If I plug in a 1, sure enough, I get 1 plus 3, that's 4. Square root of 4 is 2. 2 times 2 is 4. So final answer for this one, you get 4. I did just say seconds ago that it should work. That's not necessarily true. Sometimes you might have to do L'Hopital a few times over. In this case, I noted that the numerator was linear. Usually happens when you have like a polynomial of a higher degree, and you got to do it a few times in that instance. Here we only had to do it once. Limit as x approaches infinity. Uh, 4x squared times e to the negative x. All right. It doesn't appear to be a fraction or a ratio of two separate functions. What we should do to start it, we should just simply rewrite it and create a fraction somehow, some way. In this scenario, it's not that hard to create a fraction of this. I see a negative exponent. Let's just make it positive by bringing it down in the denominator. That's an easy fix. Numerator remains the same after that. Sure enough, if I plug in infinity, I get infinity up top and infinity down below. So that's where I'm going to make the statement in blue. Since the limit as x approaches infinity of 4x squared is equal to infinity. Likewise, the limit as x approaches infinity of e to the x is equal to infinity. This implies we can use L'Hopital use his rule. Even though it's not his. You guys know the story, right? It was one of the Bernoulli brothers that ended up actually coming up with this rule, and I think he just bought it. Anyway, so don't give him the credit. We're going to set this equal to, now taking the derivatives of top and bottom. Up top, derivative of 4x squared is pretty easy, that's just 8x. Down below, derivative of e to the x is just e to the x, and wait a minute. Bad news, we got to do this again, because plugging in infinity for both of these, you still, yet again, get infinity over infinity. One thing I will say is that it was abundantly obvious from the start, though, what the answer really is. You should know the answer without any of this stuff. Think about it, right? We got e to the x, which grows ultra super mega fast. And then you got 4x squared, which grows normal fast. And now it's growing not quite as fast. And then it's just going to be a constant. E to the x is just way faster. If you got a super fast thing and a not so fast thing, this number is going to be huge when this number is not that big. So not that big over huge is 0. And we're about to see that, so spoiled the answer here. Let's do one more L'Hopital. No, I didn't use L'Hopital here. I used L'Hopital here. Let's do one more L'Hopital. And I don't feel like writing this jazz twice over, but man, I don't know. On an AP exam, I would probably play it safe, and I'd do the same exact thing. We know that this goes to infinity and that goes to infinity. Let's take the derivative one last time of top and bottom. Derivative of 8x is just 8, and derivative of e to the x is e to the x. Now very clearly here, if I plug in like infinity for x, this is going to explode, and 8's just going to remain 8. So you can't apply L'Hopital anymore. Reason why is when you plug in infinity to this expression, up top you just get the number 8, and down below you get e to the infinity, which is infinity, and that's no longer infinity over infinity. This expression, if we were to plug in infinity here, this gets ultra mega big, and you just have 8 up top. So 8 over the biggest number possible ever forever is just 0. It would be 0.00000 and an infinite amount of zeros thereafter. So for this one, we had to apply L'Hopital twice. Yeah, a little annoying, and it does happen, or tend to happen when you have higher powers in play. So here we had an x squared. All right, for the last one, this one gets a little. You can make L'Hopital problems pretty tough, and I think this one kind of gets to that point. So the limit as x approaches 0 from the right, that's what the plus means, of 3 tangent x times natural log x. Okay, looking at this, I want to somehow, some way make it a fraction, and my winner is tangent, right? Reciprocal functions, cotangent, that's what you were thinking. So what I can do is I can rewrite this just by using basic trig as 3 natural log x over cotangent of x. All right, on first glance, it looks like a problem that you can't do because natural log of 0 and cotangent of 0 are both undefined. However, we're coming in from the right, which means referencing the graphs might be helpful. The graph for natural log of x looks a little like this. And the graph for cotangent x looks a little like this. Yeah, it's got like a bunch of waves to it. It does this forever in both directions. Yeah, we'll say that's good enough. So, taking a look at the limits via a graph makes things a little bit easier. So knowing the graphs is nice here. Since the limit as x approaches 0 from the right of 3 natural log x, looking at that graph, you can throw a 3 in front if you want to. It doesn't do too much, but stretch it out. The limit's going to be the same. It's just going to be, well, you're approaching it from the right, it's going to be negative infinity. It's going to go down forever at that point. So negative in front of that. And the limit as x approaches 0 from the right of cotangent x, looking at the graph over there, coming in from the right, we are going up towards positive infinity. This is a situation, you guys can hear my Discord. This is a situation where we can apply L'Hopital, so negative infinity over infinity is the last of the three main cases. There are other ways to get indeterminants, but these are the three that I'm covering at least, I guess. We can apply L'Hopital. All right, let's do that. So I'm going to do it over here. I'm going to say, well, this is equal to, by L'Hopital, the limit as x approaches 0 from the right of, okay, so derivative of natural log of x is just 1 over x, so this is going to be 3 over x, over derivative of cotangent x is negative cosecant square x. Yeah, okay, that's fun. Can we now directly sub in 0? No is the answer to that. If I try to plug in 0 here, I get 3 over 0 up top, and that's just not going to be helpful. And if I keep taking, this is going to be a serious issue here. If I wanted to keep applying L'Hopital, it's not going to be helpful, because you're going to notice that the numerator is always going to be infinity. Because if I plug in 0 here, that's like infinity. If I take the derivative of this, my power of x gets larger and larger in the denominator. I never escape that infinity in terms of my numerator. I never escape infinity or negative infinity. So with that said, I don't think L'Hopital again is going to help us here. What I should do is algebra. Let's just simply rewrite this and hope that rewrite will help us see things again. And maybe we might have to do L'Hopital again, but with a rewrite instead. So I want to start first by, so we're not going to jump straight to that part of the board yet, because I probably will need it. I want to find a way to rewrite this in a clever way. I'm going to merge a few things together. So first thing I'm going to do is I'm going to merge these two things underneath the same denominator, and I'm going to bring this negative up top, just to kind of forget about it for now. So I'm going to have negative 3 over x times cosecant square x, and that's just one way I can rewrite it. And if I continue with this line of thought, man, what can I do next? Reciprocal of cosecant, that will be sine, so I can write this using sine now. So more algebra, I'll say this is equal to the limit as x approaches 0 to the right, or from the right, of negative 3 sine square x over x. If I plug in 0, sine of 0 is 0. If I plug in 0, 0 is 0. L'Hopital one more time. Again, I would probably write this all over again, but as you can see, I'm kind of running out of room on the board here. So I'm going to say one more L'Hopital. So you would go through this jazz all over again. So 3 problems in a row now. I think they all had to do with multiple L'Hopitals, or at least 2 of them. I can't remember at this point. So derivative of numerator. A little bit of chain rule, so I guess I'll put it over here. I'll do it in purple. Yeah, we'll do that. So d dx of, I'm going to write this in a clever way. I'm going to write it as negative 3 times sine x all squared. This is going to allow me to see a derivative pretty easily here. I'm going to use a power rule at first, so it's going to be negative 6 times sine x. But then I also want to use chain rule inside of it. I have to find the derivative of sine, which is cosine. So here, cosine x. Alright, so rewriting the limit as x approaches 0 from the right of, it's now going to be negative 6 sine x cosine x. Derivative of x, that's the easy one. That's just 1. Finally, if I were to just direct sub in this 0, this function's doesn't have any crazy behavior in terms of considering the direction we're coming in from. If I just plug in 0, this is going to be 0 because sine of 0 is 0, so the fact that this is 1 doesn't really matter. I'm going to get 0 up top and a 1 down below. All that work just to get that the answer is 0. Yeah, that was fun. So that's L'Hopital's rule in all of its glory. I'm going to ask you to continue to math on. I will do the same. I'll see you in the next video.